we'll be starting with the Hermite polynomial. In mathematics, the Hermite polynomial falls in the category of classical orthogonal polynomial sequence which occurs in probability such as Edwards series, combinatorics, and in physics in eigenstates of quantum harmonic oscillator. Hermite polynomials are named in honor of Charles Hermite, who in 1864 identified the Hermite polynomials. They were first identified by the Laplace in 1810 and later by Chapshu, but their works were overlooked. So, starting with the Hermite's equation. Hermite equation is given by y double dash minus 2xy dash plus 2xy equals 0. So the polynomial solution of this equation are called the Hermite polynomial. So trying this as the y of x, that is summation of n equals 0 to infinity a and x to the power n. So by putting that equation in the by putting that polynomial in the equation, we'll get summation n equals 2 to infinity n into n minus 1 a and x to the power n minus 2 and so on. So so we'll try to bring them on the same platform, that is rewriting this in the form that we get x to the power n common from the equation. So by rewriting this equation, we'll get summation n equals 0 to infinity n plus 2 n plus 1 a n plus 2 plus 2 lambda minus n and a and x to the power n equals 0. So for getting the recurrence relation, we have to we want this term to vanish. So equating n plus 2 n plus 2 n plus 1 an plus 2 plus 2 times lambda minus n an equals 0. So we can rewrite this in this form: an plus 2 equals minus 2 times lambda minus n an n plus 2 into n plus 1. So here, by putting taking the values of n as even numbers, that is n equals 0, n equals 0, n equals 1, and so on. So when we take n equals 0, we get a2 equals minus 2 times lambda minus 0, that is minus 2 times lambda into a0, as n is 0, upon 2 into 1. So here the value of a2 is minus 2 times lambda 2 into 1 a0. Similarly, we get the value of a4 equals minus 2 times lambda minus 2 into minus 2 times lambda 4 into 3, that is 4 factorial into a0. So now we can write our y, taking the values of n as even numbers, as y equals a0 times 1 minus 2 lambda 2 factorial x square, similarly x to the power 4, and this will continue for the even powers of x. Alternative, will be getting the minus and plus signs. So for the value of lambda equals 0, we get y equals a0. For lambda equals 2, we get this as the y, and similarly for the lambda equals 4, we get this as a y. So now what we want is, for the highest power of x, we want the coefficient of that x to be the to the square of the power of that x. So for getting that solution, we have to take a0 equals 1, a0 equals minus 2, and for this equation we will be taking a0 equals to 12. So by taking this, we get our Hermite polynomial set for, as you can see, for lambda equals 0, for lambda equals 2, and lambda equals 4. At 0x equals, here it's the value of lambda, which is 0, 1, lambda value is 2, then we'll be getting 4x square minus 2. For the lambda equals 4, we'll be getting 16x to the power 4 minus 48x square plus 12. As you all can clearly see, that whatever the coefficient of x is, the square of the power of that x. Similarly, we can do this for the odd values of lambda and n. In this way, we get other Hermite polynomials. So here we end our discussion on Hermite polynomials. Thank you. Hello everyone. So starting with the Laguerre polynomial. Edmund Laguerre, 1834 to 1886, introduced Laguerre polynomials, which are the solution of Laguerre's equation. Our Laguerre's equation is given by x d2y by dx square plus 1 minus x dy by dx plus ny equals 0. Laguerre polynomials are used to numerically compute integrals of the form integration 0 to infinity f of x e to the power minus dx in Cauchy quadrature. So in quantum mechanics, they are seen in the radial part of the solution of the Schrodinger equation for a one electron atom. They are also used to describe the static Winchell function of oscillator systems in quantum mechanics in phase space. So Lagrange equation of order n is defined as we have defined them earlier also. So when we take the Frobenius method to solve the equation, we take y equals summation m equals 0 infinity cm x to the power k plus m, where c naught not equals to 0. So we will see that this polynomial will satisfy this equation, hence in this way we get the Lagrange polynomial. The polynomial equation which satisfies the Lagrange equation is called the Lagrange polynomial. So we correspondingly find the dy by dx, d2y by dx square and substitute this in this equation. So by substituting this, what the equation will get is this, the equation number 3. By simplifying equation number 3 further, we'll get the equation number 4. So the integral equation is this integral. The equation number 4 is obtained by equating. So by equating this, so for finding the integral equation, what will we do? This will take the smallest power of x. So you can clearly see we get the smallest power of x from this part, that is x to the power k plus m minus. Here we'll starting from the x to the power k plus m. So the smallest power of x will get from this part. So by substituting by taking the smallest power of x and equating it to the 0, so doing this we'll get c naught into k square equals 0, as we have already mentioned that c naught not equals to 0. So the option, so the only k, so it implies that k is 0. So the two possible solution of k is 0 and 0 only. So we now equate the coefficient of x to the power k plus m minus 1 to 0 in equation 4 and get cm k plus m whole square minus cm minus 1 into k plus m minus 1 minus n equals 0, and from this we'll get the equation 5, that is the recurrence relation. Now in this case the two independent solutions are given by y at the k equals 0 and del y by del k at k equals 0. As we will further see, the del y by del k at k equals 0 equals summation m equals 0 to infinity cm x to the k plus m log x, but as we know that log x is not defined at x equals 0, so we will go with y at k equals 0. So our y is summation m equals 0 to infinity cm x to the 0. So finding c, and as we know we have already find the in equation 5 that cm equals k plus m minus 1 minus n k plus m whole square into cm minus 1. So substituting k equals 0 in equation 5, what the value of cm will get is this value, equation number 7. So in equation number 7 we will be substituting m equals 1 2 3 and so on until infinity, and we'll get the various values of c1 c2 c3 and so on, and later we'll that is from the recurrence relation we'll try to generalize that c, and the generalized equation is this: cr equals minus 1 to the power r and to n minus 1 to so on n minus r plus 1 upon r factorial whole square in times c naught. So from this equation, as you can clearly see, when you put r equal r's value greater than n, and the n minus r plus 1 becomes 0 and so on, this equation will become 0. So cn plus 1 cn plus 2 cn plus 3 and so on equals to 0. So the equation 6 reduces to y equals c naught r equals 0 to infinity, and later we can simplify this to r equals 0 to n, because as we know the value for r equals r greater than n, this term will become 0. So now further we simplified this to the equation 10, and by taking c naught equals if we take c naught equals to 1, then this ln x we get ln x as this, and if we take c naught equals n factorial, we get ln x as this equation. So Lagrange polynomial of order n is given by this equation, and therefore we can find the other values of other values as putting n equals 0, n equals 1 and so on. So here we end our discussion on Lagrange polynomial. So now starting with the moment of inertia matrix, let's first consider a rigid body. And O as the origin. Ra is the position vector of the ith particle of the mass dm, and omega is our angular velocity. Considering the axis of rotation parallel to omega, we'll find the dri by dt. So as dri by dt is given by the equation, it equals dri by dt equals omega into ri. So dri by dt denotes the velocity vector of the ith particle, and as we know that velocity vector of the ith particle is perpendicular both to omega and ri. So this omega cross ri will give us magnitude as well as direction. So the total angular momentum of the body about the origin is given by the equation summation I equals 1 to n mi ri in cross dri by dt, and further simplify this equation we'll get this equation, and further we can write this rl in this term in the matrix form for getting the value of lx, ly, lz. So now what we see is this matrix is called the inertia matrix or tensor. The quantities ix, iy, iz are called moment of inertia of the x, y and z axis. Ix, y, ix, z and are called products of inertia. We can find the ix's, iyy by this equations, izz, ixy, iyz using this equation, and you will see that ix's and we will see that I-axis is called the moment of inertia, but the x-axis Iy is called the moment of inertia, but the y-axis Ixy is called the xy product of inertia, Iyz and so on. Others are called. Note that Ij values is known as the moment of inertia tensor, and each component of the moment of inertia tensor can be written as either a sum over the separate mass elements or as an integral over the infinitesimal mass elements. Now moving to the rocket mechanics, giving a little introduction. Rockets are propelled by the momentum reaction of the exhaust gas expelled from the tail. Since this gases arise from the reaction of the fuels carried in the rocks of the rocket, the mass of the rocket is not constant but decreases, the fuel is expanded. And you can this is the ideal rocket equation. You can further read about the ideal rocket equation in the sport, and the terms I have also explained the terms of the equation, that is delta v, mass fraction, applicability and so on. Now coming directly to the proof of the rocket equation by Lagrangian and Hamiltonian. As we know that Lagrangian equals kinetic energy minus potential energy, and as we know our kinetic energy is given by half mx dot square plus y dot square plus z dot square minus potential energy in terms of it depends on position vector given by xy, depends on xyz coordinates. So by directly using the Lagrangian equation, that is equal to d by dt del l by del q dot equals del l by del q. So putting del by del q dot equals m times q naught and differentiated with respect to time, which in turn which in turn equals minus del v by del q, and this term will becomes q double, so it implies that q double dot equals minus 1 by m del v by del q. So for a free particle who's under no potential energy, v equals 0. So in similar way del v by del q equals 0, and so q double dot equals 0. However, we have to account for the fact that the propulsion comes from a force which is not derived from an external potential, just like friction. So we have to treat this separately by adding an additional term to the right hand side, that equals to the minus fq. So finally our rocket's motion equation is given by d by dt of del l by del q dot equals minus del v by del q minus fq. Similarly, we can find the Hamiltonian equation by putting, as we know, h equals t plus v, taking t as half m plus v times xyz, and we know the Hamiltonian's equation set is minus del h by del r vector equals dp vector by dt, and the second equation, which is del h by del p vector equals dr vector by dt. So through this equation we can similarly find the Hamiltonian equation. Thank you.